Chapter 2 in our textbook is entitled Atoms, Molecules, and Ions. Over the next few lessons, we're going to understand the nature of atoms, how atoms combine in order to form molecules, and how atoms gain or lose electrons in order to become ions. Here we see some names and chemical symbols of some common elements. Aluminum, for example, has the chemical symbol of Al. Carbon has the chemical symbol of a capital C. And for the most part, the chemical symbol seems to be some shortened version of the name of the element. Now, there are a few instances where we may see a departure from that. If you look at gold, for example, the chemical symbol is Au. Whenever we encounter this type of anomaly, it's because the chemical symbol is based off of the Latin name of the element. So the Latin word for gold was aurum, A-U-R-U-M. If you look at mercury, whose chemical symbol is Hg, the Latin name for mercury was hydrargyrum. I know it's a mouthful, but it is what it is. Silver, the chemical symbol is Ag. The Latin word for silver is argentum. It turns out that there's a particular South American country whose discoverers saw that it was plentiful in silver. Hence, they named that country Argentina, literally meaning the land of silver. Now, what is it about an atom of aluminum or an atom of potassium or an atom of nickel that differentiates it from the other atoms? All matter is composed of atoms. Now, an atom is the tiniest unit that is representative of an element. If we were to take a brick of gold and we were to cut that brick of gold in half, then we would get two smaller bricks of gold. If we were to take one of those and to cut it in half, and then 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 cut it in half until we were only able to get down to the particle that we couldn't cut in half anymore. That particle would be an atom. Now, an atom is made up of three subatomic particles of protons, neutrons, and electrons. Inside the heart of the atom, at the very center of the atom, we find an area where over 99.99% of the mass of an atom can be found. That area we call the nucleus. Inside the nucleus is where we find the protons and the neutrons. Since they are both found inside the nucleus, we classify these types of particles as nucleons. The electrons we find around the nucleus in the area of the atom that isn't the nucleus. And in a moment, we're going to take a look at the similarities and differences between protons, neutrons, and electrons. We're ultimately going to see that electrons and protons both carry a charge while a neutron does not. If you look at the chart, we see that a proton has a mass of approximately 1 atomic mass unit. Now that is a very, very small unit of measurement. An atomic mass unit is equal to 1.66 times 10 to the negative 24th grams. That's a very small unit, but the mass of a proton is a very, very small measurement. Similarly, we see that a neutron has a mass of about 1 atomic mass unit. An electron, however, is significantly smaller. It is nearly 2,000 times smaller than a proton or a neutron. So one way in which protons and neutrons are similar is that they have a similar mass, but they differ from electrons with respect to mass. We spoke of charge a moment ago. The charge on a proton is positive. A proton is a particle that carries a charge of +1. An electron is a particle that carries a charge of -1. So that charge is equal but opposite in sign to that of a proton. And a neutron, as you might suspect, having the same roots as the word neutral, carries no charge. I mentioned that protons and neutrons are both found inside the nucleus, while electrons are found outside the nucleus. So what does this have to do with an atom of carbon versus an atom of copper? The atomic number of an element, the number by which the periodic table is organized, that number represents the number of protons in the nucleus of an atom of a given element. So, for example, an atom of boron, element number 5, has 5 protons inside its nucleus. Follow along with me as we drop down. An atom of element number 13, aluminum, has 13 protons inside its nucleus. Let's scoot to the right. An atom of silicon, element number 14, has 14 protons inside its nucleus. Now, an atom must have the same number of protons as electrons. An atom must have the same amount of positive charge as it does negative charge. That positive and negative charge must balance out in an atom. So that atom of boron that has 5 protons inside the nucleus, it has 5 electrons outside of the nucleus. That atom of silicon that has 14 protons inside the nucleus has 14 electrons outside of the nucleus. Now that says nothing about the number of neutrons, and there's a reason for this. The number of protons is given by the atomic number. The number of electrons is the same as the atomic number. But the number of neutrons can vary from atom to atom. There are different types of atoms of various elements. For example, magnesium. Every single atom of magnesium, element number 12 on the periodic table, every single atom of magnesium anywhere in the universe, if you look inside of its nucleus, you're going to find 12 protons. If you look around the nucleus, you're going to find 12 electrons. But there are 3 naturally occurring types of magnesium atoms. And how do they differ? Well, they differ in the number of neutrons. One of these types of magnesium has 12 neutrons inside the nucleus. One has 13 neutrons, and yet still another has 14 neutrons. These 3 types of magnesium atoms are called isotopes. Isotopes are atoms of a given element that differ in the number of neutrons. And of the 118 elements on the periodic table, there are several elements that have multiple isotopes. Now there are some that only have one. Potassium, element number 19. There's only one stable, naturally occurring isotope of potassium. Similarly, fluorine, element number 9. There's only one naturally occurring isotope of fluorine. But I just mentioned magnesium, and there are 3 isotopes of magnesium, element number 12. There are 3 isotopes of hydrogen, element number 1. There are 10 different isotopes of element number 50, 10. So there are 10 different isotopes of 10. Now what do they all have in common? They all have 50 protons inside the nucleus and 50 electrons outside the nucleus. But they vary in the number of neutrons. How are we supposed to know this? We don't. You can't look at the periodic table and say, oh, this isotope, or excuse me, this element has 5 isotopes. This element only has 1 isotope. But these isotopes differ in the number of neutrons, and because of this, they differ in mass. An atom of carbon that has 6 neutrons is not going to be as massive as an atom of carbon that has 7 neutrons. And that's not going to be as massive as an atom of carbon that has 8 neutrons. Now, they're all carbon atoms, but they have different masses. At the bottom of this slide, we see designation by which we can determine the atomic makeup of an isotope. X represents the chemical symbol. The letter A in the upper left-hand corner represents the mass number, which is the total number of protons and neutrons. And the letter Z in the lower left-hand corner represents the atomic number. So if we were referring to that isotope of carbon that has 6 protons and 7 neutrons, then the chemical symbol would be a capital C. In the bottom left-hand corner, the atomic number would be 6. And in the upper left-hand corner, the total number of protons and neutrons, 6 plus 7, would be 13. So looking at that designation, we would see a 13 on top of a 6 with the letter C as the chemical symbol. Now, in the designation that we see here, oftentimes the atomic number can be omitted. As I've mentioned, some of the elements have multiple isotopes. Carbon, for example, having carbon-12, carbon-13, and carbon-14. These isotopes can also be written with the name of the element followed by the mass number, carbon-12, carbon-13, and carbon-14, respectively. Isotopes of a single element have the same chemical properties. They don't differ in the nature of their chemical reactivity, but they do differ in mass. The reactivity of an atom is based on the number of electrons, and we know that that is the same as the number of protons, and within a given element, the number of protons and electrons doesn't change. Here we see the 3 isotopes of hydrogen, hydrogen 1, hydrogen 2, and hydrogen 3. Hydrogen 1 has 1 proton inside the nucleus and no neutrons. Hydrogen 2 has 1 proton and 1 neutron, and hydrogen 3 has 1 proton and 2 neutrons. The fact that the atomic number of hydrogen is 1 means that if you look inside the nucleus of an atom and you see 1 proton, guess what? It's hydrogen. The number of neutrons is what varies between isotopes. Now, out of all of the elements on the periodic table, most of them are referred to by their chemical name and their mass number. For example, iron 56 refers to an atom of iron that has 26 protons and 30 neutrons. Carbon 14 refers to an atom of carbon that has 6 protons and 8 neutrons. But hydrogen is the only element on the periodic table whose isotopes have special names. Hydrogen 1 is referred to as protium, hydrogen 2 is referred to as deuterium, and hydrogen 3 is tritium. Here we see a portion of the left-hand side of the periodic table, and in each box we see the element's name, the atomic number. Underneath that we see the chemical symbol, and underneath that we see yet another number, a number that we refer to as the atomic weight or the atomic mass. Now, I don't want you to confuse that with the mass number. The mass number does not appear on your periodic table. If you'll remember, the mass number refers to the total number of protons and neutrons in an isotope of a given element. And if an element has multiple isotopes, for example, calcium has 5 different isotopes. So we can't place 5 different numbers to speak to the total number of protons and neutrons in each type of calcium atom. So what does that atomic weight refer to? We'll talk about that in just a moment. But if we want to determine the composition of an atom, well, by knowing its atomic number, we immediately know the number of protons in the atom. If we know the atomic number, then we also know the number of electrons in the atom. And if we are given its mass number, then we can subtract the atomic number from the mass number to get the number of neutrons. If you think about it this way, if the number of protons and neutrons is the mass number, and then we subtract the atomic number, which is simply the number of protons, then we will end up with the number of neutrons. So here we see an example of fluorine 19, which has 9 protons, 9 electrons, and the number 19 refers to the total number of protons and neutrons. If 9 of those are protons, then the remaining 10 must be neutrons. The atomic mass, or the atomic weight, refers to the average mass of all of the naturally occurring atoms of a given element. But you have to take into consideration the abundance of each isotope. For example, in the universe, there's some hydrogen 1, there's some hydrogen 2, and there's some hydrogen 3. If I were to ask you what the mass of an atom of hydrogen is, well, it would depend on whether we were talking about hydrogen 1, hydrogen 2, or hydrogen 3. Hydrogen 1 has a mass of approximately 1 atomic mass unit. Hydrogen 2 has a mass of approximately 2 atomic mass units, and hydrogen 3, you guessed it, approximately 3 atomic mass units. So, how much does an atom of hydrogen weigh? Well, once again, it depends. Instead, we refer to the average weight or the average mass of an atom by taking into consideration that most of the hydrogen in the universe is hydrogen 1. Over 98% of the hydrogen in the universe is hydrogen 1. The atomic weight of hydrogen reflects that in that that overall average looks a lot more like the number 1 than it does 2 or 3. The atomic weight of hydrogen is 1.0079 atomic mass units. So when we take all of the atoms of hydrogen in the universe and we add them all up and we divide by the total number of atoms, then we end up with a number that's much closer to 1 than it is to 3, because most of the hydrogen in the universe is hydrogen 1. Now, this is not to be confused with the atomic number. This is not to be confused with the mass number. And typically, this does not refer to the mass of an atom, since many atoms have multiple isotopes. If you look underneath carbon on your periodic table, you'll see the number 12.011, which suggests that the average mass of an atom of carbon is a little more than 12 atomic mass units. Well, if carbon 12 has a mass of about 12 atomic mass units, and carbon 13 atomic mass units, and carbon 14 atomic mass units. If we average all of their masses together and we end up with 12.011, then that might suggest that most of the carbon in the universe is carbon 12. In order to determine the atomic weight or the atomic mass of an element, we need to know a few things. First, we need to know the exact mass of each isotope. Now, up to this point, you've heard me refer to the approximate mass. Hydrogen 1 weighs approximately 1 atomic mass unit. Hydrogen 2 weighs approximately 2 atomic mass units. But for us to do this type of calculation and determination, we need to know the exact mass of each isotope. Now, this is not information that we have swimming around in our heads. This is information that would have to be supplied to you. We also need to know the abundance of each isotope in nature. In other words, in a sample of 100% of all of the chlorine, element number 17, how much or what percentage of that is a particular isotope? Chlorine is made up of 2 isotopes, chlorine 35 and chlorine 37. Of all of the chlorine in the universe, 76% of all chlorine is chlorine 35. The remaining 24% is chlorine 37. So for us to do this type of calculation, we're going to see a problem set up very similar to the one that we see at the bottom of the slide. I'll read it verbatim. Boron is made up of two isotopes, boron 10 and boron 11. The exact mass of boron 10 is 10.013 atomic mass units, and the exact mass of boron 11 is 11.009 atomic mass units. Of all the boron in the universe, 19.9% is boron 10, while the remaining 80.1% is boron 11. Calculate the atomic weight of boron. Well, when given that information, that's all the information that we need in order to solve this type of problem. If you take the exact mass of each isotope and you multiply it by its abundance as a percentage divided by 100, then you will get each isotope's contribution to the overall weighted average, or the atomic mass. So 11.009 atomic mass units times 80.1% divided by 100% gives us 8.818 atomic mass units. That is the contribution of boron 11 to the overall weighted average. The contribution of boron 10 is 1.992587 atomic mass units. Once you do this, add those two values together. Or if you have 5 isotopes, do it for each of the 5 isotopes and add those 5 numbers together. And the number that you come up with, the sum of those contributions, is going to be the weighted average, or the atomic weight. If you look on your periodic table underneath boron, I will bet you that it reads 10.811. Suggesting that the average mass of an atom of boron is 10.811 atomic mass units. Now, it should be noted, there is no atom of boron anywhere in the universe that weighs exactly 10.811 atomic mass units. That's not what the atomic weight tells us. It's not the weight of a particular atom. It is the average weight of all of the atoms of a particular element, taking into consideration that some isotopes are more abundant than others.